Today we'll talk about equation of motion. Equation of motion allows us to calculate coordinate of final position if we know coordinate of initial position, initial velocity vector, its magnitude and direction, and acceleration vector, its magnitude and direction, and time. I will teach you how to write equation of motion if the body is moving with constant speed, or it uniformly accelerates or uniformly decelerates. Uniform motion will be just a special case of uniformly accelerated or uniformly decelerated motion, for which magnitude of acceleration vector is equal to 0. So, we don't have to additionally derive equation of motion in this case. You can see here name of axis, coordinate of initial position, coordinate of final position, displacement, initial velocity vector, acceleration vector, and distance. So, we have four possibilities. First, uniformly accelerated rectilinear motion in the x-axis direction. You can see it here. In this case, acceleration vector is directed the same as velocity vector. You can see it here. Second possibility, it is uniformly decelerated rectilinear motion in the x-axis direction. You can see it here. In this case, acceleration vector is opposite to velocity vector. You can see it here. Third possibility, it is uniformly accelerated rectilinear motion in the direction opposite to x-axis. You can see it here. In this case, acceleration vector is directed the same as velocity vector. You can see it here. The last possibility, it is uniformly decelerated rectilinear motion in the direction opposite to x-axis. You can see it here. In this case, acceleration vector is opposite to velocity vector. You can see it here. To derive equations of motion, we only need equation for distance in uniformly accelerated and uniformly decelerated motion. Here we have uniformly accelerated rectilinear motion in the direction of x-axis. Coordinate of final position equals x0 plus distance d. It is equation for distance in this case. So, coordinate of final position equals this. Here we have uniformly decelerated rectilinear motion in the direction of x-axis. Coordinate of final position equals x0 plus distance d. It is equation for distance. So, coordinate of final position equals to this. Here we have uniformly accelerated rectilinear motion in the direction opposite to x-axis. Coordinate of final position in this case equals x0 minus distance d. x0 minus distance d. It is equation for distance. So, coordinate of final position is equal to this. And the last possibility, we have here uniformly decelerated rectilinear motion in the direction opposite to x-axis. Coordinate of final position is equal to x0 minus distance d. It is equation for distance. So, coordinate of final position equals this. We see that if velocity vector or acceleration vector are directed the same as x-axis, we have plus here or here. When these vectors are opposite to x-axis, we have minus here or here. Here or here. If we change definition of V0 and A in these equations to coordinates of V0 vector and acceleration vector, then we will have always this equation. And here there always will be plus. We should remember that coordinates of vector are equal magnitude of vector if vector is directed the same as axis, or minus magnitude of vector if vector is opposite to the axis. So, in these equations, V0 and A are coordinates of vectors V0 and A, so they can be positive or negative. In next lessons, I will show you applications of equation of motion. It is really helpful in tasks in which we have to calculate position and time after which two bodies will meet. Then it is enough to write equations of motion for both bodies and calculate time and coordinate of final position from these equations. So, it is the end of this lesson. Subscribe if you think I helped you. Today we'll talk about applications of equation of motion. During last lesson I derived most general form of equation of motion for uniformly accelerated and uniformly decelerated rectilinear motion. Then I said that equation for uniform motion we get if we put A, I mean acceleration, equal to 0 in this equation. In today's task, we have two cars moving along straight line with constant speed. The first car departed from city A towards city C at 2 o'clock at 20 km per hour. The second car started from city B towards city C after 1 hour at 80 km per hour. The locations of the cities and their distances are shown in the drawing below. It is here, not below. Write the equations of motion for both cars, assuming that the coordinate of the city C is equal to 0. What time and where will the vehicles meet? The drawing is part of the data. Distance between cities A and B is equal to 400 kilometers. It's here. B and A. And distance between cities A and C is equal to 200 kilometers. A and C, 200 kilometers. To write equations of motion, we draw x-axis. It's here. Coordinate of city C is equal 0. So coordinate of city A is equal minus 200 kilometers and coordinate of city B is equal to minus 600 kilometers. Coordinate of city A is equal initial coordinate of position of first car x01. It's here. And coordinate of city B is equal to initial coordinate of position of second car x02. It's here. Here we have general form of equation of motion. T minus t0 is just time of motion. T is what clock shows in this moment, and t0 is initial time at the clock. If both cars began to move at the same time, and at the beginning the clock showed 0, we could replace t minus t0 by t. But not in this case, because cars began to move not at the same time. Cars move with constant speed, so acceleration is equal to 0. So the third expression in this equation is equal to 0. x0 is initial coordinate of position, and v is magnitude of velocity vector. In front of v, we write plus if velocity vector is directed the same as axis, or minus if velocity vector is opposite to the axis. Vectors v1 here and v2 here are directed the same as x-axis, so in both equations of motion there will be plus in front of v here. Let's write the data. Magnitude of velocity vector v1 is equal 20 kilometers per hour here. And magnitude of velocity vector v2 is equal 80 kilometers per hour here. First car began to move at 2 o'clock here. Second, 1 hour later, so at 3 o'clock here. Coordinates of initial positions of cars equal to minus 200 and minus 600 kilometers. It's here. We see it here and here. Now we can write equation of motion for first car. Here is plus, because velocity vector v1 is directed the same as x-axis. You can see it here, v1 and x-axis. We put data to this equation and we have final equation here. That's final equation. We do the same for second car. Here is plus, because velocity vector v2 is directed the same as x-axis. You can see it here, v2 and x-axis. We put data to this equation, and here we have final equation of motion for second car. Here, final equation. These two equations allow us to calculate coordinate of position of both cars at an hour if we put this hour here, here, or here. When they meet, the coordinates of the position on the x-axis will be the same. So, x1 equals to x. We put here right sides of equations of motion and calculate time the cars met. Cars will meet at 10 o'clock. Not 10 hours later. First car begin to move at 2 o'clock, so he has been moving for 10 minus 2, this is 8 hours. Second car departed at 3 o'clock, so he has been moving for 10 minus 3, this is 7 hours. Now we can calculate coordinate of position of the place they met. It is enough to put 10 hour to one of equations of motion. It is done here and here. We see that the vehicles will meet at the coordinate minus 40 kilometers on the x-axis. Now we can solve this task graphically. In this table, we will calculate coordinates of position for both cars. We can put time to equations of motion here and here. But we know that first car at 2 o'clock was in the city A, so its coordinate of position equaled to minus 200 kilometers. And second car at 3 o'clock was in city B, so its coordinate of position equaled to minus 600 kilometers. Every hour, the coordinate of position of first car increased by 20 kilometers and second car by 80 kilometers. So we can add 20 here and 80 here. Now we can represent the motion of cars in xt coordinate system. We read the time and coordinate of the intersection of the lines representing the movement of both cars. It will be time and coordinate of the place where the cars met. So, we solved our problem. So, it is the end of this lesson. Today I want to teach you how to solve tasks from physics in which we have to find the place where a thrown object will hit the obstacle. This obstacle usually is some hill. You can see it here. That's the hill. Or horizontal platform. You can see it here is platform. Or vertical wall. It's here. The idea of this method is simple. We will try to write equation of the path of the thrown body in x-way coordinate system and write equation of the line describing the obstacle. Next, we will find coordinates x and y for the point that belongs to both lines. To find equation of the path of thrown body, we can use equation of motion. It is here. In this equation, x0 is coordinate of initial position. U0 is initial velocity. Exactly speaking, it is coordinate of this vector. Coordinate of a vector is equal the value of vector if a vector is directed the same as axis, or minus value of vector if it is opposite to the axis. A in this equation is coordinate of acceleration vector, so it can be positive or negative. We can write equations of motion independently for direction of axis x and y. To do it, we have to replace velocity vector v0 by components of this vector in the direction of axis x and y. Here there is v0y and here is v0x, components of the vector v0. These components are directed the same as axis x and y, so their coordinates are positive. Acceleration vector is directed vertically to the ground, so its coordinate in the direction of axis y is negative. You can see it here. Value of coordinate of acceleration vector equals minus g, where g is gravitational field strength. It has the same value as the acceleration due to gravity near the surface of Earth. We choose x and y for initial position of thrown body equal to 0. We have to express v0x and v0y by v0 and sine and cosine of alpha. It's done here. Now we can write equation of motion for the x-axis and y-axis. For x-axis, x0 and a are equal 0, and u0 is equal plus v0x. So, the equation of motion in the direction of axis x looks like this. X equals v0x times t. For y-axis, y0 is 0, u0 is equal plus v0y, and a is equal minus g. And here we have equation of motion for the axis y. So, we have two equations of motion, and we get rid of t from these equations. It's done here. Next, we replace v0x by v0 times cosine of alpha and v0y by v0 times sine of alpha. It's done here and here. Instead of sine of alpha divided by cosine of alpha, we can write tangent of alpha. It's here. Instead of this, now we have equation of path of the thrown body. It's here. Now it is enough to write equation describing the obstacle and combine these two equations to find the coordinates of the point that is part of these two lines. If the obstacle is a hill, its equation is just equation of straight line y equals ax plus b, where a is tangent beta and b is 0. So, equation of the hill is y equals tangent beta times x. You have it here too. So, we have equation of the path of the thrown object here, and equation of the obstacle of this hill. It's here, and we put right side of the second equation to the left side of the first equation. It's done here. Next, we take all these expressions to left side and change form to this. Left side is equal to 0 if x equals to 0. This is the place from which we throw our body. The second solution was what we were looking for. If we put this value to first or to the second equation, we can calculate the value of y. If the obstacle is a platform parallel to the ground, then its equation is just y equals h. You have it here and here. Now it's enough to put the right side of the second equation to the left side of the first equation. We've done it here. And take all these expressions to the left side. As you can see, we have quadratic equation, and we can calculate roots of this equation. If the obstacle is a vertical wall, its equation is just x equals L. Have it here and here. We put this value to right side of the first equation and calculate value of y. So, we have solved our problem, and it is the end of this lesson. Today we'll talk about examples of application of Newton's laws of motion. We'll start with simple problems and then move on to more complex problems. Let's start with a body resting on a flat horizontal surface. It's here. We have to draw all forces acting on that body. It is weight, here, W. It is normal force, R, often called reaction force, here. Weight tries to accelerate the body in the direction perpendicular to the surface. Due to that, the body pushes the surface with force of pressure, Fp, here. Force of pressure. According to Newton's third law of motion, if there is action, there is reaction, so the ground exerts upward force on the body, normal force, R. The body remains at rest, so according to Newton's first law of motion, weight and force of reaction, so-called normal force, balance each other. Reaction force and weight. These forces balance each other. These vectors are opposite to each other, but their magnitudes are the same. Normal force and pressure force are opposite to each other and have the same magnitudes according to Newton's third law of motion. Pressure force and the reaction force. These forces act on different bodies, so they do not balance each other. So, three forces, weight, W, reaction force, R, and pressure force, Fp, have the same magnitudes. Magnitude of weight equals mass multiplied by g. You can see it here, where g is gravitational field strength. It is equal acceleration due to gravity. So, pressure force is also equal to mass times g. If this body is moving in the direction parallel to the surface and there is no friction, velocity will not change, because in the horizontal direction no force acts on the body, and in the vertical direction the same forces act as before, which balance each other. You can see it here. We have the same forces in vertical direction. For weight and normal force balance each other, and there is no force in the horizontal direction. So velocity does not change, because resultant force is equal to 0. The resultant force is equal to 0, so according to Newton's second law of motion, acceleration is equal to 0. It means that velocity vector does not change. The body moves in a uniform rectilinear motion. Now, if we add external force F, you can see it here, in horizontal direction, then we have all forces that acted before and which balance each other, and external force, which is now resultant force. We have the same forces as before here. These two, weight and normal force, balance each other, and we have external force F in the horizontal direction, and this is also resultant force. Acceleration vector will be equal to external force divided by mass, and will be directed the same as external force. In both cases, when the body was initially at rest or it was moving, the body will move in uniformly accelerated rectilinear motion. Magnitude of acceleration is equal magnitude of external force divided by mass. You can see it here. If we add friction force, it doesn't change forces acting in vertical direction. You can see it here, the same forces. And here friction force, external force, velocity and acceleration. In horizontal direction, resultant force vector will be sum of external force and friction force, so it will be directed the same as external force, because external force has greater magnitude than friction force. Magnitude of resultant force will be equal to difference of magnitude of external force and friction force. Still, it would be uniformly accelerated rectilinear motion. Now, we'll try to calculate acceleration of bodies connected by a light inextensible string on a smooth plane. Horizontal force F, we can call it external force also, is applied to the first body, and we assume that there is no friction. In vertical direction, we have weight W2, W1 and reaction forces R1, R2 and pressure forces FP1, FP2, here and here. pressure forces don't act on these bodies. Weight and normal forces balance each other in both cases, so resultant forces acting on first and second body depend only on horizontal forces. External force tries to accelerate first body. This body is pulling second body by the string with force N2. According to Newton's third law of motion, second body exerts a force on first body, N1. Forces N1 and N2 are opposite to each other. They have the same magnitudes. The speed of the first body increases, so magnitude of external force F is greater than magnitude of N1 force. We write Newton's second law of motion independently for first and second body. Here and here. Acceleration of first and second body is the same, so instead of A1 and A2, we'll write just A. Instead of N1 and N2, we'll write N. At first, we'll find resultant force vectors Fr1, Fr2. Resultant force 1 is equal to sum of weight W1, normal force R1, external force F, and N1. External force N1, normal force, and weight. Weight W1 and normal force R1 cancel each other, so resultant force vector Fr1 equals F plus N1. And magnitude of this vector is equal to magnitude of F minus magnitude of N, because F and N1 are opposite to each other. Resultant force Fr2 equals to weight W2 plus normal force R2 plus N2. Weight and normal force cancel each other, so it is equal to N2. And magnitude of resultant force Fr2 equals N. It is sum of N2, R2, W2. These two forces balances each other, so they cancel in this equation, and we have only N2. So, to these equations, instead of Fr1, we put F minus N here, and instead Fr2, we put N. It's done here. Now we can get rid of these equations N. We can add left sides of these equations and right sides. It's done here and here. And we see that N and N cancel each other. So we can calculate from this equation magnitude of acceleration. It's done here. We see that we could treat these bodies as one body, and forces N1 and 2 would be just internal forces which don't influence movement of the whole body. Then, resultant force acting on that body would be just external force F. To calculate magnitude of acceleration, it would be enough to divide magnitude of external force F by mass of the whole body, m1 plus m2. I think that it is enough for first lesson about applications of Newton's laws of motion. During next lessons, we'll analyze more complex problems. So, it is the end of this lesson. Subscribe if you think that I helped you. We all want to be appreciated by other people, but usually we don't appreciate other people ourselves. World would be much better if we were not so selfish. Today we'll talk about inclined plane. We'll try to calculate acceleration and final velocity for the block sliding down the incline, and we'll calculate acceleration and height at which the block launched at the bottom of the inclined plane will stop. In both cases, we assume that there is friction. So, we have a block sliding down the ramp with friction. We have to draw all forces acting on the block. It is weight here. It is reaction force here, often called normal force, and friction force here. Reaction force R is perpendicular to the ramp. It balances component of weight perpendicular to the incline, W2. We'll talk about it later. Friction force, FF, is always opposite to velocity and parallel to the ramp. It would be much easier to analyze the problem if we replace weight vector by its components W1 and W2. The first is parallel to the ramp and the second is perpendicular to the ramp. The effect of these components is the same as that of weight, W. Components of the vector don't have to be perpendicular, but usually they are. To find components of a vector, we draw directions of components from the beginning of the vector B. Next, we draw from the end of vector B lines parallel to these directions, here and here. In the points where these lines cross directions of components, there will be ends of components, here and here. I have to remind you how we add vectors which are parallel and have the same direction. You can see it here. vector A and vector B. We see that magnitude of vector C in this case is equal magnitude of vector A plus magnitude of vector B. Here. If vectors A and B have opposite directions, magnitude of vector C, which is sum of vectors A and B, is equal magnitude of A minus magnitude of B. You can see it here. So now we are prepared to solve our problem. Firstly, we draw vector of weight W here. It is perpendicular to the horizontal. Its magnitude W equals mass multiplied by G, where G is gravitational field strength. It is equal to acceleration of bodies due to gravity. Next, we draw components of weight W1 and W2. Component W1 tries to accelerate the block down the ramp, and component W2 pushes the block in the direction perpendicular to the incline, and as a result, block pushes the incline with force Fp, pressure force. Here. Magnitudes of component W2 and normal force R are the same according to Newton's first law of motion. Reaction force and pressure force have the same magnitude according to Newton's third law of motion. Here and here. So, all three vectors, component W2, normal force R, and pressure force Fp, have the same magnitude. R, Fp, W2, Fp, W2. W is weight vector, W1 and W2 are components of weight vector, Fp is pressure force, R is reaction force, Ff is friction force, Fr is resultant force, μ is coefficient of friction. We write Newton's second law of motion in vector form, here. And for magnitudes, here. We transformed this last equation to this form. We calculate from it acceleration. Firstly, we'll find resultant force vector, here. It is sum of weight, normal force, and friction force. We can replace weight by its components. W2 and normal force cancel each other, so resultant force is equal W1 plus friction force. It's here. These vectors are opposite to each other, so magnitude of resultant force is equal magnitude of W1 minus magnitude of friction force. Here. Now we have to express magnitude of W1 and friction force by mass, g, and sine and cosine of alpha. Friction force is equal coefficient of friction times force of pressure. Pressure force is equal magnitude of W2. We can find angle alpha in these triangles. Sum of angles in a triangle is 180 degrees, so this angle between inclined plane and weight is equal 90 degrees minus alpha. This angle is the same as angle between component W1 and weight. This angle. This angle is equal 90 degrees minus this angle, so this angle is equal alpha. We can calculate sine and cosine of alpha from this triangle. Sine of alpha is equal magnitude of W1 divided by magnitude of weight. Cosine of alpha is equal magnitude of W2 divided by weight, magnitude of weight. You can see it here and here. We transform these equations so we could calculate W1 and W2. Magnitude of weight is equal mass multiplied by g. We put it here and here. Friction force is equal coefficient of friction multiplied by pressure force, Fp. You can see it here. Pressure force is equal magnitude of W2. So we can put here m times g times cosine of alpha. Now we put W1 and force of friction to equation for resultant force here. It's done here. You can change form of this equation to this. Next, we put resultant force to Newton's second law of motion. It's here. We can get rid of mass from this equation, and we have last equation. If there is no friction, it means coefficient of friction equals to 0, this is 0, so acceleration equals g times sine of alpha. In our equations, a is magnitude of acceleration vector, so it is always positive, even if the block slowed down, as will be the case when the block will be moving upward the incline. Usually in tasks we are asked to calculate acceleration and final speed of the block at the bottom of the incline. To find final speed, we have to write equations for acceleration and distance in uniformly accelerated motion. It's here and here. Initial velocity is equal 0, so these equations change form to this and this. We get rid time from these equations and find equation for v2, final velocity. It's done here and here. Instead of a, we put value of a. Usually we don't know the distance d, but we know height of the incline h. So we express d by h. They are connected by sine of alpha. You can see it here. So d is equal h divided by sine of alpha. We put d to this equation and we have such equation. If there is no friction, coefficient of friction is equal to 0. So it is 0. 0 times cosine of alpha is also 0, and we can get rid of sine of alpha then. We see that in this case, final velocity does not depend on angle alpha. We shouldn't be surprised, because if there is no friction, mechanical energy is conserved, and we know that potential energy depends only on mass and height of the body. So we solved first problem. If we launch the block upward the incline, at the bottom of the ramp, only velocity and friction force, that is always opposite to velocity, will change directions. Resultant force still will be directed down the incline, and acceleration vector is always directed the same as resultant force, so it is also directed down the incline. Component W1 and friction force Ff are directed the same, so in equation for magnitude of resultant force there will be plus instead of minus. You can see it here. W1 and friction force have the same direction, and here is plus. Also, in last equation, for magnitude of acceleration, plus will be instead of minus. Here. and here. If there is no friction, coefficient of friction equals to 0 and acceleration equals g multiplied by sine of alpha. In this task, we want to calculate height at which block stops, so we write equations for magnitude of acceleration and for distance in uniformly decelerated linear motion. Find equation for acceleration and for distance. Final velocity v2 is equal to 0, so it will vanish from first equation. Second equation will not change. Now we get rid time from these two equations. It's done here. And we replace distance by height divided by sine of alpha. And we calculate from this equation height. If there is no friction, coefficient of friction is equal to 0. So, in this equation, mi is equal 0, 0 multiplied by cosine of alpha is equal to 0, so we have such equation, and we can get rid of sine of alpha from this equation. We see that if there is no friction, height does not depend on angle alpha. So we solved our problems. So it is the end of this lesson.